Hello, good morning, good evening, good afternoon, everybody, wherever you may be. Hola, 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 hola. And so welcome to this Zoom talk, which is supported at three places. Our speaker is in France. Our regular lecture room is in Warsaw, Poland, but we are hosting it from Brazil, from Florida, or also known as Florianopolis. So without any further ado, I'm giving the floor to HERVÉ, our today's speaker, OYONO-OYONO, and he will tell us everything and more about geometric decomposability for groupoids. The Zoom is yours. Thank you.
Okay, thank you very much for the invitation. So it's a great pleasure to give this talk to your online seminar. And so the title of my talk is Geometric Decomposability for Groupoids. And the motivation for this is the Novikov conjecture. And so let me recall briefly the statement of this conjecture. On basically, if I start with a finitely generated group, and if you consider the Stonechurch compactification of this group, just recall that this is just the spectrum of the bounded function from gamma to C, and there is this result of Exxon, which was proved by three proof of this result. One by Exxon, another one by Jean-Ly Tu, and another one by Guoyang-Yu, that if the group, if the action on the Stone compactification of gamma is amenable, I will come back later on the definition of this and what is an amenable action. Then gamma satisfies the Novikov conjecture. And what is this conjecture? If you start with a compact-oriented manifold which have gamma as a fundamental group, then the higher signature are homotopy invariant. And the higher signature this number, this is a pairing of a class in cohomology. You pair this class with a homology class, and so your manifold is oriented, so it has a fundamental class. There is another characterized class that arises from this manifold, which is called the Pontryagin Hirzebruch class, and you can perform the cap product. This class, this Pontryagin Hirzebruch class, is a class of cohomology, so you can partially integrate, and then you obtain a class in homology, and you can pull back it by the classifying map, and you pair it with your element X in cohomology, and you obtain a number, a rational number, which is called a higher signature. And the Novikov conjecture state that this should be an homotopy invariant. Okay. And to the point, there is there was this approach. This theorem can of Ixon on U can be viewed as the end of the approach by Kasparov using gamma element and KK theory and things like this. So this proof is very analytic. It uses some infinite dimension analysis, and at the opposite there is so this give there's a lot of this give a lot of example, almost all there's a classical example come from this can be included in this can be viewed as a consequence of this result. At the opposite, there is an approach which is more geometric by Guolong-Yu, which is completely opposite because this one, the previous one used infinite dimension analysis, and this one only use analysis on finite metric space. So this is completely opposite because so on one hand you have analysis on space with infinite dimension, and here you basically you just have finite set. So this is really different, and the approach is completely different, and is more geometric. And what you prove is indeed the Novikov conjecture for group with finite asymptotic dimension. So what is asymptotic dimension? We say that a proper metric space has asymptotic dimension equal to m if for every positive number it can be covered by m+1 subset that each of these subset can be written as a R disjoint union of uniformly bounded family of a subset of X. So what does it mean? This means that this is a disjoint union, and each subset in this disjoint union are at a distance more than R, and the diameter of this family of subsets is uniformly bounded. Okay, so the typical example is Z. Okay, so if you start with a positive number, then you can write Z as a union of two subsets. One is in blue and the other one is in red. Okay, and the blue part can be written, can be decomposed as a disjoint union of a finite subset of a fixed cardinal, and each copy is a distance more than R from another. Okay. Okay, so example. Okay, there was a lot of example of such a space. Just recall first the definition. Z to the power m has a asymptotic dimension equal to n. Okay. And Gromov hyperbolic spaces also have finite asymptotic dimension. And more general, also discrete subgroup of Lie groups also have finite asymptotic dimension. So we have quite a lot of example. Okay. Okay, so now. So indeed, Guolong-Yu proved the Novikov conjecture with group with finite asymptotic dimension. So you have to see group as a metric space. So how does it go? You start with a symmetric generating system, and then from this there is a length. The length of an element of the group is just the minimum number of generator in S you need to write your element as a product. And from this length you can obtain an invariant metric, a left invariant metric. And the result of Guolong-Yu is if you start with a finitely generated group, and if the metric if as a metric space it has a finite asymptotic dimension, And there is a technical condition that the classifying space must have the homotopy type of a finite cedulary complex. Then under this assumption, then the group gamma satisfies the Novikov conjecture. Okay. Okay, so the key indeed the key point to prove this result is the notion of decomposability for family. So what is decomposability for family? If you start with two family of a subset of a given metric space on a positive number, okay, then you say that the first family is decomposable with respect to the second one if for each metric space in the first one, it can be written as the union of two subsets such that each of these subsets is are the disjoint union of a family of elements if in the second family. Okay? So, example, if for any positive number, the single family X is decomposable with respect to a uniformly bounded family, this exactly means that X has a asymptotic dimension equal to 1, okay, because this means that with the previous definition, we had m plus 1, if m was the dimension, then X has to be decomposed into the union of m plus 1 subset. So here m plus 1 is equal to 2, so m is equal to 1. Okay, so this exactly means that X has an asymptotic dimension. Okay, and then if you start with a single family, then you can do the process again. I can give you another number, and then decompose the new family, and then you have another family, and it can be given another number, and then decompose again. And okay, if the asymptotic dimension is finite, then this means that you will decompose your single family in a fixed number of steps into a uniformly bounded family. Okay, so the number of steps only depends on the asymptotic dimension. Okay, and then you can if you have a winning strategy to decompose your single family using in the same game, then you will say that that your space has finite decomposition complexity. Okay, and so okay, so we have two approach of the Novikov conjecture. The first one is okay by studying the action of gamma on its Stonehenge compactification, and the other one is using this decomposition. And okay, I would like what I would like to do is to understand the decomposability of this metric space in terms of some decomposability of the action of the group gamma on the Stonehenge compactification. But it's not clear what does it mean the decomposition of an action of a group, because okay, the first thing you can imagine to decompose an action is to have invariant subsets. But if the action on the Stonehenge compactification is not Okay, it's quite difficult to understand. There might be okay. It's difficult to have an idea of what should be invariant subset. And most of the time, when you have action, you don't have invariant subset. So probably the notion of action is too rigid for decomposition. So the first thing is what does it mean decomposability of the action? So in terms of group action, if you stay inside the framework of group action, this is not flexible enough. So you have to introduce the notion of groupoid. So the groupoid are more flexible for this kind of thing that you want. So briefly, let me recall what is the definition of a groupoid. So groupoid can be seen as a set of arrows. Typically, let me define first example, which is the action groupoid. If you start with an action of a group on the set X, then you can define the action groupoid in this way. This is the set of triple X gamma Y that X is equal to gamma Y. And the point is you can see this triple, you can see this element of the groupoid as arrows. So if you have a triple like this, so the first element is called the range, and the other is the source. Okay, and you see element in your groupoid as arrow going from the source Y to the range X. Okay. And what you can do is you can compose two arrows in such a way, okay? If the range of the second arrow coincide with the source of the first one, then you can compose it, okay? And this composition is associative, okay? And you have some units. Okay, and it acts as a unit. This means that if you compose with a unit, you're just doing nothing on the left or on the right. Okay, and you also have an inverse. Okay, like this. When you compose on the right by the inverse, then you obtain the unit on the source. On the left, the unit on the range. On the left, you obtain the unit of the source. Okay, so this is the action groupoid. I don't know if you have questions so far.
I don't think so, no.
Okay, so we can define now what is a general groupoid. We just keep the arrow. Okay, the idea is the groupoid is a set of arrow with the same the same rule. You just forget the gamma. So groupoid is given by pairs. G is the arrow, X is the space of units. And you have two maps as before, the range on the source, okay? You have units which are section for S on R, and so you see units as before. Units as before will be represented as dot, and you have a composition which is associative and defined on the set of a composable pair. So pair is composable if the source of the first coincide with the range of the second one. And then you have a composition as for the action groupoid, and the unit acts as a unit on the left, on the right. Okay, just exactly as before. You just forget the group, and you have an inverse. Okay, and it's exactly as before. Okay. So the idea is to see a groupoid as arrows, okay, and this is really a generalization of the group action, okay, and this gives you a much more flexible framework for decomposition, okay. So let me start with so first, give you some example of groupoid. The first one, of course, is a group. So we already know an example, which is the group action. A group is a groupoid with the space of units as only one element. And another, indeed, I will only use three kind of groupoid. So the first one is the action groupoid. We have already seen. The second one is the pairs groupoid. Okay. So the pair groupoid is okay. Pair groupoid is just the pair on two pair are composable if the range of the second one is equal to the source of the first one. Okay. And the inverse is just swapping the two elements in the couple. Okay. And there is an example which is a little bit more involved, but not that much. Is you can parameterize your pairs groupoid with another set, and then you obtain the family of pair groupoid. Okay, so you have just a family. Y give you the fiber. Okay, and for each y you have a pair groupoid. Okay, so point-wise, this is a pair groupoid, and you parameterize it by y. So basically, this will be the groupoid I will use in this. We'll see in this talk. Okay. So now let me give you an example of geometrical decomposition for groupoid. So maybe first, okay, I have to put some topology. So groupoid is locally compact if G is locally compact and X is locally compact, and we require the structure maps to be continuous. Okay. In this talk, all the groupoid will be Hausdorff. This means that G is Hausdorff and X is Hausdorff, and all the groupoid will be locally compact on Hausdorff indeed. Okay. And if it is étal, if moreover the structure, the range map and the source map are étal. Okay. In the example we will see, we'll have étal groupoid indeed. And in this case, you can see the space of unit as an open subset in G. Okay, using the unit. And so the example of locally compact groupoid, if you start with a locally compact space, then the pair groupoid is also locally compact. Okay, and if X is discrete, then the pair groupoid is étal.
And I understand that when you say locally compact, you actually mean locally compact Hausdorff.
Yes, yes, Osdorf now, yes, in French, locally,
I know. That's
locally
why I'm
compact,
now drawing attention. Because
Osdorf.
in English, we have to add
Yes, I
alter.
know, I know. But
Okay,
all the Groupoid in this talk will be Osdorf.
cool.
Will be locally compact on Osdorf.
Thanks.
Okay. Okay. And if you start with an action groupoid, so if G is locally compact acting on the locally compact space, so everything is Osdorf, then your action groupoid is locally compact. And if if G is discrete, then your action groupoid is étal. Okay. Okay, so this is the general definition for groupoids. And okay, now we can go to an example of decomposition. So I don't really need to know exactly what is the Stone-Church compactification. Okay, it's not really beautiful. It's not a very nice space. But the only thing that we need is that it's some limit of point in Z, okay.
If I might drop in for the sake of students, you can very easily think about the checksum compactification through Gelfand-Naimark. I mean, you take your locally compact space, and instead of taking functions vanishing at infinity, you take all bounded functions. And you get a unit of sister algebra. So it must be the sister algebra compact outer space. And that's exactly Stone-Church. I'm sorry, it's an obvious remark for experts, but there are at least 4 students.
Okay, yeah, thank you. Thank you.
So according to this remark, maybe I would also say something that this is not the same. This corresponds, those points in Stone-Church compactification corresponds to linear multiplicative functionals, and this corresponds to taking limits with respect to so-called ultra filters. And this should not be confused with the so-called generalized limit, the so-called Banach limit, which is also important in the context of amenable groups.
Okay. Thank you. Okay. Indeed, basically, we really need a few things. But we don't on the Stone-Church compactification. Okay. What we basically need is that Z is dense. Is dense in the compactification, and then in some sense the distance is preserved when you go to infinity. So you can see indeed this groupoid action as limit. So this limit of point in Z such that the difference is equal to n to the which is in the middle. Okay. So this is really what is really important. The description of the decomposition I will give to you. So for a positive number R, you consider the set of elements in the groupoid such that the n is a length less than R. Okay, as an absolute value less than R. And let me go back to the composition we saw at the beginning when we gave an example of a space with asymptotic dimension equal to 1. So we have this decomposition, and let me name the copy of the subset you obtain in this decomposition. And then I can enlarge a little bit this decomposition on the definition. Okay, and then so you take for each copy, then you take the set of elements which is a distance less than r from this copy. You obtain again a family of disjoint subset of Z with this choice of n. Okay, and then you can define, you can consider GI, which is the set of triple that which are that x on x prime are obtained as limits of y on y prime, which set in the same copy of the finite subset. Okay. So this means that why you have, so they are of course at a distance less than r. Okay. So of course, if for example, if you start with an element which is in blue, for example, and if y is in blue, and if y prime is at a distance less than r because of your choice of n, then the second element y prime will be also in blue, in the blue enlarged subset. Okay. So this means that basically, if you start with an element in the groupoid action with length less than r, then it's in one of the two copy, G1 or G2. Okay, because it has to, you can, if you write so it's a limit of point y on y prime, you can choose all the element y in the limit to be in the blue part, for example, or on the red part, and this means that the other element will be also in the blue part, in the corresponding blue part or red part. So this means that at the end you will be in G1 or in G2. Okay. So this is clear. This decomposition. Because this is the key point indeed. This is what I want to generalize.
Okay, you want to generalize it from the group of integers to an arbitrary discrete group, or do we have some
to an arbitrary groupoid?
Groupoids. Okay.
Groupoids, yes. To generalize this to any groupoids indeed.
So it doesn't have to be an action groupoid, right?
No.
Okay, so that is just a source of examples. Okay. Mm-hmm.
Okay. So a point is that G1 on G2 a restriction of a groupoid. So G1 on G2 a groupoid indeed. Okay. So the first thing to notice. So the first point is that all the element of length. So GR can be seen as the elements with length less than R, and element of length less than R can be written as decomposition of two groupoids. Okay. And so just just recall the definition I introduced in the previous slides. And now if y on Y prime are in the same subset, the same subset, the finite subset in blue or in red. Then this is a subgroupoid. Indeed, when in the composition, you can just forget the n in the middle. So you just end up with a pair groupoid. Okay, okay, you can forget the n and the composition. You just have the composition of a pair groupoid. Okay, so by the end, by taking the limit, you have just a parametrization by the parametrization of your finite subset. Okay, so this means that indeed you obtain by the end a family of pair groupoid. Okay, for GI is isomorphic to a family of pair groupoid. Okay. So this means that the set of elements with length less than r sit in the union of two groupoids which are isomorphic to family of pair groupoid, and it's parameterized by something which is compact. Okay, so this is a compact groupoid. Okay, so what I did is that I write the element of length less than r as the union of two compact groupoids. Okay, it's quite easy to see that they are also open indeed, because this is okay. Your space, Stonehenge compactification is totally disconnected. So this is not. This is quite easy to see that these two subgroupoids are open. So what I did so far. I write. You can see that G, the element of length less than r, sit in the union of two compact open subgroupoid. Okay. And so this is much more. Okay, this means that basically you can see element. Every element of a given order as sitting in compact open groupoid. Okay, so this is exactly this kind of decomposition that I want to generalize. Okay. So for sake of simplicity, I will. Okay, this can be indeed the decomposition can be this can be done in the general case of locally compact Hausdorff groupoid. But for sake of simplicity, let me focus on of groupoid provided with a length. So what is the length on the groupoid? It's like for group, it's a function from G to R plus which vanish on unit, and so LG is equal to 0 if and only if G is a unit, and you want the length to be symmetric. And there is if you have two pairs which are composable, then the length of the product is less than the sum of the length. Okay. So example, if you start with the length on the group, then you can this provide a length on your action groupoid, like we did indeed for the action of Z on in Stonehenge compactification. And for pair groupoid, if you start with a discrete metric space, that then the distance give you a length on the pair groupoid. Okay, and from now maybe at the end I will if I have time I will come back to the general case. But we will assume that the groupoid is étal, so locally compact and Hausdorff, and is provided with a proper length. Okay, this means that it's as a function this is proper. The pullback compact to compact. We will assume that the space of units is compact and second countable. Okay, but indeed everything can be done in full generality, but it's much more simple to write things in this framework. Okay. Okay. So what is the decomposition of an étal groupoid? So with this assumption. I start with an étal groupoid, and so take a subgroupoid of G with a space of unit Y on the positive number R. So what is an R decomposition for H? This is a quadruple given by two open subset which cover the space of unit. And H1 and H2 are a groupoid, a subgroupoid of H. And we require this groupoid to be open in G. Okay. And what you require is that the element of H which have one leg in V1 or V2, then if it has a leg in if it have this source in Vi, then it have to sit in Hi. Okay. So since Hi is a groupoid, this is also true for R. So this means that once you have a leg in Vi, then you are in Hi. Okay. And so this is what is R decomposition, and what we have seen with the action of Z on is stone change compactification is that for every positive number, then you have a R decomposition into two compact open subgroupoid. Okay, so this is the generalization of what I wrote down before for the action of Z on its stone change compactification. Okay. Okay, so this is the definition, the generalization of what I wrote before for the action of Z on its stone change compactification. And now, if I start with a set of open subgroupoid of G, we see that we say that subgroupoid is decomposable if for each positive number you have R decomposition with the groupoid in this subset in this set of subgroupoid of G. Okay. And we say that D is closed under a coarse decomposition if using this process, you cannot add more subgroupoid. Okay, this means that any subgroupoid which is decomposable is already in D. Okay, using this process, you cannot add more groupoid. Okay, and now we can, if you start with a family of open subgroupoid of G, you can consider the smallest set of open subgroupoid of G, which is closed on the coarse decomposition, and that contains D. Okay. Basically, this is the smallest subset of groupoid you can obtain by coarse decomposition from element of D. And we say that an open subgroupoid has finite D decomposition complexity if H belongs to the closure of D on the coarse decomposition.
It's just a naive question, if I may. If I look at this operation, does it have properties similar to the closure operation? Like how it behaves with respect to intersection, unions? I mean, after all, we are talking about a set of open subgroupoids. So,
what do you mean by?
Yeah, you can have a union of such sets, intersection. Do you have usual properties of what would have for the closure operation?
I don't know. I have no idea.
I've got you.
No idea.
Okay.
Okay.
It might be obvious.
I won't really. Okay, probably the only thing you need in some special case is to be the only operation that probably you will do is for D is to be closed maybe on the taking subset, but okay, you don't use a lot of you don't really use.
No, it was just a side question, and because one has to be careful when you are talking about say graph sister algebras. You talk about ideals in graph sister algebras. You have, in terms of graphs, you have so-called saturation operation.
Yeah.
But this saturation operation, even though it seems so deeply related to the closure, it is not satisfying the axioms of the closure. So, okay. Sorry for Peter.
Okay. Okay, so example, as we have seen, if I start with the action of Z on instantial compactification, then it has a finite D decomposition with respect to the set D of its compact open subgroupoid. Indeed, you can have a decomposition in one step. Okay, and basically, this property is property of asymptotic dimension equal to 1. So the free group, for the same reason as Z, basically has also asymptotic dimension equal to 1. So it's also decomposed in one step into a compact open subgroupoid. So it has a finite D decomposition complexity with respect to the set of its compact open subgroupoid. And I introduce the notion of finite decomposition complexity with this decomposition game. And then if as a metric, if you start with a finitely generated group, and if as a metric space it has a finite asymptotic dimension, it has finite decomposition complexity, then the groupoid action will have a finite D decomposition complexity with respect to the set of its compact open subgroupoid. So this includes, for example, a countable subgroup of Lie groups, and Gromov hyperbolic group, and the countable subgroup of GLN of K, local field K. Okay, so the first application I will give is application to amenability. So let me recall what is a groupoid amenability. So let me give the definition of the fiber, of the R fiber of an element. G upper X is the R fiber of an element X in X. And we see that G is amenable, is amenable groupoid if there exists a net of continuous and positive and compactly supported function on G. Such that you can consider the L1 you can consider the L1 norm on each R fiber, and the L1 norm has to be less than 1, okay? And this fiber, this L1 norm on each fiber has to converge uniformly to 1 on compact subset of X, okay? So you really see that this sum as L1. You have similar definition for the amenability of a group. So you really see that as the L1 norm on the fiber. And okay, and it has to be the L1 norm has to be quasi-invariant uniformly on compact subset of G. Okay. So this is the definitions of amenability for groupoid, which extend the notion of amenability for group. Okay. And we said that the action of gamma on X is amenable if the groupoid action is amenable. And,
sorry, could you elaborate in what sense you take this limit in point 2?
In point 2?
Yes. You have it, something goes to 1 uniformly on compact subsets. I'm trying to imagine how exactly you are doing it.
The limit is in J. You start
okay, so what is your okay. Okay, so this is J because this is a net. Okay.
J is
okay. Here it's just less, and then okay, I've got it. Thank you.
Okay. Okay, so okay. No, the action on the Stone-Church compactification indeed capture amenable action. This means that if there exists an amenable action on the compact set, then if only if the action on the Stone-Church compactification is amenable. And we say that in this case that the group is amenable at infinity, and so the result, as I mentioned at the beginning, is that if a group is amenable at infinity, then it satisfies Novikov conjecture. Okay. And okay, example of amenable action in action of amenable group, and if I take a locally compact group and an amenable and closed subgroup, then any discrete subgroup act amenably on G mod P. And okay, for the group, you can choose P that G mod P is compact. So this means that discrete subgroup of the group is amenable at infinity. So action of growth hyperbolic on the boundary are amenable, and the action out Fn is also amenable at affinity. Okay. Okay. So so what is the point is groupoid decomposition stable on the amenability is stable on the groupoid decomposition. So maybe I don't know. I have to go back a little bit. Okay. Maybe what was the definition? I just forget to give the definition of so what I mean by so finite dynamical complexity is to have a finite decomposition with respect to a set of compact subset. Okay, this is the conclusion of the proposition. Is my definition of the finite dynamical complexity. I forget to put it on the slides. Okay, so the result of there is a result of sorry. This result of Gantner will let on you that if G has finite dynamical complexity, this means that G is decomposable with respect to a family of compact on open subgroupoid. Then G is amenable, and this result indeed can be extended to heredity of amenability on the groupoid decomposition. Okay, so this result of Gantner will let on you give you that if you start with a group with a finite decomposition complexity, then it's amenable at affinity. Okay. And then this result of Gantner will let you can be generalized. If you start with an étal groupoid with finite decomposition complexity with respect to a family of open and amenable groupoid, then G is amenable. Okay, so this is the first application I wanted to give to this decomposition of groupoid. So indeed, this groupoid decomposition was introduced at the beginning for question of K-theory, and for question of K computability. So the question. So basically, for the Novikov conjecture, you have to compute. You have to compute the approach, the Ixon approach, approach of this Novikov conjecture was to compute some K theory of a cross product of some action groupoid. And I want to apply this decomposability to this computation. So from a groupoid, first there is the sister algebra, the reduced sister algebra of this groupoid. So you can define a convolution so if you start with the function, the complex function continuous and compactly supported on G. Then there is a convolution product. And you obtain also an evolution. This is basically the same formula that you have for groups. The only thing is you have to perform this product on the fiber. And there is a completion process, and you end up with basically which is the same. And for group, and you obtain the reduced sister algebra of G, and you can also do the same thing with coefficient, and you obtain the reduced cross product. So G algebra basically this is the sister algebra of a continuous section on upper semi-continuous sister algebra bundle, and you assume that you have an action of the groupoid. So the action is fiber-wise, so you have some continuity condition. Then you can
wait. So X is the unit space of a groupoid G, right?
Yes.
Okay.
Yes. So you can. There is an action on fibers indeed, and then you can pull back this bundle using R. Okay, and then you can consider a continuous section of this pullback. Okay, with compact support, And then you can exactly as we did before. Then you can there is a convolution product. Okay. Okay, the things match together, and then you obtain a product, and you can exactly as for group action, then you can define an adjoint on the completion, and then you obtain the reduced cross product in the same way. Basically, okay, for group for action groupoid, this correspond to the group cross product. Okay. And what I want to do some K-theory computation on this.
Sorry, I'm confused by your convolution formula.
Yes.
Don't you have something wrong here?
Yes, here. Okay. Yeah. Yeah. So the range is in the fiber of the R range of gamma prime, which is R gamma.
Well, but wait, I mean, F and G are just numerical functions, right? They're going to.
No, they're valued in a C-star bundle.
Sorry, the point is that this algebra of bundle of algebras is acted on by the groupoid.
Yes.
Okay.
You can each AX is a C-star algebra. Each fiber is a C-star algebra. Okay.
Yeah, but the point is that this G, gamma acts on G of gamma prime inverse.
Gamma prime. So this go to the fiber at the source of gamma prime. So the source of gamma prime to the fiber at the range of gamma prime.
Yeah.
So you have at the source of gamma prime you have a C-star algebra. At the range you have another C-star algebra. And gamma prime is the fiber at the source to the fiber at the range. Okay. It's like vector bundle.
It's like an equivariant vector bundle. So you can say that...
Yes, it's an equivariant. It's an equivariant vector bundle. Exactly like this. It's an equivariant vector. It's an equivariant vector bundle. Okay.
Okay.
Okay. The right picture is exactly the picture of an equivariant vector bundle. Okay. And what I want to do is some K-theory computation. So if I start with an étale groupoid with a family of subgroupoid, and with a morphism of G algebra, okay, and you assume that okay, the morphism induced in K-theory by F is an isomorphism for each cross product by a subgroupoid in D. Okay. And the question is, do you have an isomorphism for the full groupoid? Okay. So you know that you have an isomorphism for a family of subgroupoid, and the question is, do you have an isomorphism for the full groupoid? Okay. And okay, so first we can start with group, which is which is easier, of course. And we start with gamma equals C, and D is a trivial subgroup. And if I start with a Z morphism, okay, and if you map F induce an isomorphism in K-theory, then it induces an isomorphism in K-theory for the cross product, and this is the Pimsner-Voekelescu six-term exact sequence. Okay. Okay. So this is the kind of problem I want to generalize to groupoid. Okay, so I have here you just have a single family, which is the trivial subgroup. But okay, you can imagine a bigger family. Of course, you want to have what you're interested in having the smallest family as possible. The same holds for the free groups. Indeed, this is the Pimsner six-term exact sequence. Okay, and this question is closely related to the Baum-Cohn conjecture. Indeed, if D is a set of the finite subgroups, then this is related to the Baum-Cohn conjecture. So probably I won't go into detail concerning the Baum-Cohn conjecture, but indeed you can take this statement as the Baum-Cohn conjecture. So just recall that there is an assembly map if you start with a group gamma acting on the C-star algebra. Then there is an assembly map, and the Baum-Cohn conjecture states that this assembly map is an isomorphism. And the Baum-Cohn conjecture with coefficient then states that this is an isomorphism for any algebra provided with an action of gamma. And,
so please correct me if I'm wrong, but I believe here for very fancy coefficients using some Gromov hyperbolic stuff, we have a counterexample, right?
Yes, exactly. Yeah. Yes. Yes. And the point is, okay, if you start with a group that satisfy the Baum-Cohn conjecture, then assume that you have a morphism of C-star algebra that induce an isomorphism for every finite cross product, every cross product by finite subgroup. Then your full cross product, the cross product by the full group will be also an isomorphism. Okay, so this is a consequence of the going down, what we call going down functors. And indeed, this is an equivalence. It was proved by Meyer and Nest. So this is an equivalence. So this can be taken as the definition of the statement of the Baum-Cohn conjecture with coefficient. Indeed. Okay. And this has been generalized to ample groupoid by a student of Siegfried Echterhoff, Christian Bonnecke, for group. So an étal groupoid is ample if the base space is if the unit space is totally disconnected. Okay. And typical example action on the Stonechev compactification of a discrete group. Okay. And in this case, you have the same result. This means that okay, if your cross product by a compact subgroupoid give you an isomorphism in K-theory, then you have an isomorphism for cross product by the full group. And for étal groupoid, we have to replace compact open subgroupoid by relatively open proper subgroupoid. What is a relatively open subgroupoid? Subgroupoid is relatively open if it's open, and if H is closed in GY, with GY is the set of elements of G with source in Y. Okay. So example of relatively open subgroupoid, if you take a saturated open subset of X, then the restriction groupoid is relatively open. Okay. On the counterexample, so if you start with the trivial bundle groupoid over 0, 1, this means at each fiber you just have the group Z mod Z2, okay? And if you remove 1 point, the point with at one extremity, which is the non-trivial element of Z mod Z2, then this groupoid is not relatively open. Okay, so this is the kind of situation that I want to avoid.
Sorry, can you go back, please?
Yes.
Can you remind me what is a saturated open subset?
This means that if it's like saturated for the action, okay. This means that if the range is in if the range is if the source is in U, then the range is in U. You cannot go. You cannot leave U using your arrow.
Okay.
In U, then
that's very much like in graphs.
Okay. 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 So I want to generalize to étal groupoid to étal groupoid, and so if I start if you start with a homomorphism which induce an isomorphism in K theory for any relatively open proper subgroupoid H of G, do you have an isomorphism for the cross product by the full groupoid? Okay, so this is just replace my compact the finite subgroup by a relatively open proper groupoid. And this is true, of course, for discrete group, for ample groupoid, and if G has a gamma element in sense of 2, this is also true. So okay, so this is okay. So this is the generalization of what we have seen for finite subgroup, and then we can apply decomposability for this question of computation in K theory. So if I start with an étal groupoid with a finite decomposition complexity with respect to family D of relatively open subgroupoid, and if I start with an equivariant morphism between two G algebra, and you assume that for every cross product by element in your in D, then you have an isomorphism. Then this means that you have an isomorphism for the cross product by the full groupoid. Okay. So this means that if you can check that you have an isomorphism for subgroupoid of your family D, then you have isomorphism for the cross product by G. Okay. And this can be you can replace morphism by element in KK theory. Okay, and you can apply this to the Bohm-Cohn conjecture indeed. So under if you start with an étal, this has to be the groupoid has to be étal. Unseparable, and if it has a finite decomposition complexity with respect to the family of relatively Klopen subgroupoid, and you assume that it has a gamma element in the sense of 2, and you assume that every element in D satisfies the Bohm-Cohn conjecture with coefficient, then G satisfies the Bohm-Cohn conjecture with coefficient. Okay, so this means that under the existence of this gamma element, then the Bohm-Cohn conjecture for groupoid is stable under geometric decomposition of groupoid. And for example, if you start with an action groupoid, and if the group has a gamma element, which is the case for a lot of most of the case, you have a gamma element for the group. Then the group action groupoid has a gamma element, and any relatively Klopen subgroupoid of the action groupoid also have a gamma element. Okay, so this gives you a lot of example of groupoid which have gamma element. Okay, so so this is for the application to K-theory, and basically the basic what is the tool to prove this kind of theorem is quantitative K-theory. So what is quantitative K-theory? Basically, you know that K-theory is defined from projection and from unitaries. And then you have to take some propagation into account, and we replace projection on unitary by quasi-projection on quasi-unitaries. So first, you have to have filtration of your sister algebra. So filtration, it's just defined, it's a family, an increasing family of linear subspaces which are closed by involution, and you have a compatibility of the filtration with respect to the product, and you have the union of your filtration is dense in B, and the example indeed of filtered sister algebra given by cross product by groupoid. If I take an étal groupoid provided with a proper length, if I take GR is a set of the element in the groupoid with length less than R, okay. And now, if the filtration indeed is given by the closure of element which are supported which have support of length less than R, okay. So this gives you a filtration on the cross product, okay. So this is really the kind of situation I want to consider. And now I can define what is almost projection on almost unitaries. There's two parameters. If I start with a filtered sister algebra, there is two parameters: the propagation and the control. The control is the defect to be a projection. Okay, so an epsilon R projection is something which is projection in norm up to epsilon. And so it is a self-adjoint, and it need to have propagation less than R. Okay, and of course it has a spectral gap around 1/2, and so it gives you by functional calculus, it gives you a projection which is close to your almost projection. And you can define this in the same way which is an almost unitary. The defect to be a unitary is controlled by epsilon, and it has to be of propagation R. And of course, these almost unitaries are invertible. And then from this I can define by replacing projection on unitaries by quasi-projection by epsilon R projection on epsilon R unitaries, I can define what I call quantitative K theory. So I can define let me define through some notation the set of epsilon projection, the set of epsilon R unitaries. So I can take the inductive limit of this epsilon R projection and the inductive limit of this epsilon R unitaries. And then once I have this, I can define nomotopy equivalence relation on projection on unitaries, exactly as we do for in K theory. We introduced exactly the same case of equivalence relation, homotopy relation. So if I take a pair of an epsilon projection on a number which can be viewed as the identity matrix on the same size, okay. And the same thing for the unitaries. So I have to be careful for unitaries. I have to allow the increasing of control on propagation if I want to have a group structure. And then I can define for epsilon on R fix the quantitative K theory as this class of equivalence of projection of unitaries. And the point is we have a abelian group as for K theory, okay? And this is done for unital C-star algebra. And okay, if it's non-unital, you just you use unitarization exactly as you're doing for K theory. Okay, so this is a way. From this you can approximate your K theory. First, you have mapped from the quantitative K theory to the K theory. Basically, there is one bracket. Okay, this is the first left bracket should not be there. So there is a map from quantitative K theory to K theory. Using the spectral projection associated to a normal projection, and same thing for so this is the odd case. On for the even case, you use the spectral projection. In the odd case, you just say that almost unitary are unitary, and every projection can be approximated by an epsilon R projection. And so for unitary you have the same thing. So you can write K theory as the limit, as an inductive limit of quantitative K theory if you fix epsilon. So this is an approximation of K theory, okay. And but it has a very important feature comparing to usual K theory is that basically you have exact in K theory to have exact sequence. Basically, you need to have ideal. For quantitative K theories, it's much more flexible, and typically in our situation, if we start with a decomposition of a groupoid, okay. Then if you consider, so you have the sequence of map, of course, which also you have this sequence, this composition of these two maps in K theory. But in K theory, this compositions has no chance to be exact because you don't have ideal, basically. Okay. So this composition in K theory has no chance to be exact. But in quantitative K theory, this composition is almost exact in the middle. Almost exact is mean that up to rescale, I can rescale the propagation, the R. I can rescale it, but by a fix. The factor is fixed, is universal. This means that up to rescale, then you have exactness. And moreover, you know that so this is this looks like the Meyer-Vittoris exact sequence in K theory, except that you don't have ideal here. Okay. Moreover, the point is that you have a boundary map. Okay, you have a boundary map. You have to increase the propagation, but you have a boundary map, and of course, in usual K theory, you have no chance to have this boundary map. Okay, you cannot even define it, but in quantitative K theory, you can define this boundary map. Okay. And this composition now is this sequence is exact something up to rescale. So this means that you can use it now. You know that you don't have this kind of sequence in K theory. But what you know that K theory can be approximated by quantitative K theory, and now in quantitative K theory you have this 6-term exact sequence, and so you can do the computation. The computation K theory can be done using this 6-term exact sequence. And this is the way you prove the result, the stability of the stability for this K theory computation on the geometric decomposition of groupoid. Okay. So it's almost the time. So I think I'm gonna stop.
Yeah, 3 minutes.
3 minutes. I just want to I assume all the groupoid the groupoid I assume that they were that the groupoid was étal, that the base space was compact and separable, and they are provided with a proper length. Indeed, you can do this computation in a much more general case, in the general case of locally compact groupoid. Okay, you just have to replace length by G order. So just give you a definition of a G order. So maybe just first introduce some definition. What is the inverse of a party of a groupoid on the fiber, the S fiber, on the R fiber. And G order is a subset of G, which is symmetric. And we need that for every the S fiber of every compact of compact. Okay. So the restriction of S to R is proper indeed. And basically, if gamma is in R, then the source, the unit corresponding to the source, is also in R, as gamma here stands for the unit corresponding to the source. Okay. And okay, and just give you example. So if G is a discrete group, then order are exactly a symmetric finite sets, okay, that contain the neutral element. And if I start with a proper metric space, then this is take a fixed R. Then the pair which have distance less than R. This means that the sets which are band which is close to diagonal, are close to diagonal, is a G order. and if you the lens, if you have a group equipped with a lens, okay, then you have if you take the element of lens less than n, this give you also an order. So this is really the straightforward generation to lens. And okay, you can define using that. You can define what is you replace your number R by order, and you can define what is a decomposition. The only thing is you have to add the existence of a partition of the unit as now your space of unit is no more separable, and now you can do everything. All the result that we had before stands replacing by using order. Then the result concerning amenability on the K compatibility on the Baum-Kohn conjecture stands in this framework. So I'm going to stop here. Thank you very much for your attention.
Okay, obrigado. All right, now we can proceed with questions. First, any questions here in Florianópolis? No? No. I'll ask my questions later. So now how about Tomek, you are clapping or asking a question?
I'm clapping.
But you can also
ask the question also.
Just switch the camera on, please.
Yes. Let me. Okay. I don't know if you can see me.
Yeah, we can see you all right.
Okay. So my question is like this. Your definition of amenability in the case of groups corresponds to the Day's condition.
Yes.
But there are several different definitions of amenability in the group case.
Okay.
Is it so for at least étale groupoids?
There's no Follner condition, for example.
Which
the Follner condition? I think the first one is for group. I think that the ones you think is the Follner condition. There's you don't have you don't have definition like the Follner the Follner condition. You don't have in terms of fixed point for
fixed point property.
You don't have this definition for groupoid, unfortunately.
For groupoid,
you don't have this.
You mean that it doesn't make sense, or it is not known?
I think that it does not make sense.
Okay.
And what else?
What about measure theoretical?
There is some okay. So there is some measure definition. So you have to see the paper of Jean Renaud, where it's very well explained. But okay, indeed, for groupoid, you will have to you will have a topology. Okay, this is for groupoid. This is what is called topological amenability.
Okay.
Which is okay.
Okay, thank you.
Okay, great. Anybody in Warsaw in room 405?
I don't think there's any question here.
Okay, thank you at all. So how about any other folks in Zoom? Adam, you always ask a question. Here's your chance.
No, but this time I don't have any questions. I'm not saying that everything, that I understood everything, but I will need to come back to this.
All right. Anybody else on Zoom would like to ask?
May I ask another question?
You're on Zoom.
It's about locally compact groupoids. the last slide.
Okay. Last one.
Is there a version of this qualitative K-theory when you don't have this length, but
yes,
you have
exactly.
this?
Indeed, for the filtration. Okay.
Yes.
Good point. Basically, if I go back to my filtration here, I can replace the positive number by orders.
By order. Okay.
And you can define. You can define you can compose there is a orders form a lattice. Okay, that's what you use, and you can you can define what is what is filtration relatively to these orders, and then you can define quantitative K-theory with respect to orders, and you also have this Meyer-Vittoris sequence in quantitative K-theory. This is exactly the same thing, but this is an important.
But how do you combine this control with this order? If these are not numbers, if they are not both numbers, then how do you combine them?
The control, you can keep the control. Basically,
you're keeping the control. Yes.
You just replace the R by the
order. Yes.
By the order.
But in this qualitative, in the exactness of these sequences, I remember there was something mixing K and epsilon.
Yes, exactly. You're right.
So how do you?
Okay. So you mean
do this in the case of the order?
Next one, does this mean?
Yeah.
K epsilon R. You can compose the order.
So simply it's okay. Now I understand. The order is an index in this K.
Okay, the K-eps, okay, I define my function as a real function, but I can define it as a integer value function, okay? And you can compose the order. If you compose an order, you obtain an order. It's a symmetric composition. You have to symmetrize the composition. And your K epsilon R is just composition.
Okay, thank you very much.
But this is a good point.
Yeah, thank you.
Okay, so let me wind it up with my two very simple-minded questions. So first one concerns your theorem about the Baum-Kohn conjecture. Could you please go back to the slide? I cannot tell you which slide it was, but you had some conclusion that...
This one?
Yes, exactly, yes. Okay, so it looks extremely beautifully conceptual, right? Because you are saying that if everything is okay for a finite decomposition complexity with respect to the family of all relatively open subgroups, then you can have a conclusion for the big guy. So my question is, using your theorem, which I repeat is conceptually very beautiful, obviously, have you managed to prove some new cases verifying the Baum-Kohn conjecture?
Not so far.
Not so far.
So the example I'm looking for is the case of if you start. So if you the point if the groupoid in D are amenable, then G is amenable. Okay. So the conjecture for amenable groupoid, the Baum-Kohn conjecture, is known. So it's not. The point is to have example with a family D as the A group property. Because the A group property for groupoid has no chance to be stable under this kind of decomposition. Okay, so okay. on probably example of groupoid. Okay, so this is one on another probably example with, but I didn't. Okay, is for example, if you take it's the action of relatively hyperbolic. So you take so this is for okay. See, let me, if I take the action groupoid of gamma on its stone change compactification. So this for this kind of example, in the case of gamma is relatively hyperbolic with respect to a family. For example, I don't know, good group. I don't know what should be the property of the group, but in this case, I think that this result apply. Okay, so probably the thing to look is probably the action of gamma of this on this stone charge compactification when the group is relatively hyperbolic with respect to a family of subgroup.
This was a very good answer. Thank you so much. That's exactly what I wanted to understand. And the last question is a very wild one. I mean, don't treat it too seriously. I'm not an expert in quantum groupoids, but I know that there has been a lot of research done in Hopf-algebroids, quantum groupoids, analytical aspects, algebraic aspects, lots of different versions. You even have Hopf-algebroid Galois theory. You have lots and lots of things. So would you give any chance that your decomposition procedure that you defined for groupoids could work for quantum groups, for quantum groupoids?
Yes, we think so.
Because, you know, the Meyer nest you mentioned, that's exactly the road to the Baum-Kohn for locally compact quantum.
So first, there is a okay. There is a version of the quantitative K theory for quantum groups. I've told you that for general for locally compact groupoid, I have to replace length by order. For groupoids, there is also a filtration, which is a filtration by basically by representation. The representation give you also a filtration. Okay, so you can define what is an order. Okay, using a representation. And you can define there is okay the definition of the Meyer-Vittoris decomposition in something which is very algebraic indeed.
Yes.
So it can be defined in a very general way and perfectly with the groupoid decomposition, but it makes sense also for quantum group.
Okay.
Quantum group action. So this is the construction of the construction of this Meyer-Vittoris exact sequence indeed is much more it's applied in a very it's more in a more general in a larger set of situations indeed. So each time there is a okay okay there is a basically we can define what is a Meyer-Vittoris pair for sister algebra with the filtration, and once you have this pair, then you have this exact sequence, and you can do a computation in K theory. So this apply basically the framework. This apply to filtration by quantum group onto quantum group action. Because in this case you have the same kind of filtration.
Okay, thank you so much. Tomek, are you still?
Yes, I have. Very interesting to investigate a little the application to quantum group.
Yeah, thank you. Tomek?
Yeah, yes, I have a question about the assembly map. What kind of construction you can apply to this, let's say, local assembly maps to obtain the global assembly map?
Excuse me?
How, okay, if you have this decomposition, then you have this, let's say, local assembly maps for this family D.
Yes.
And how can you integrate this local assembly maps to the global assembly map for the groupoid G?
That's the difficulty indeed. Basically, if you have a gamma element, basically you have some duality. So this is very easy. You need to have some duality, and that's why you need for general groupoid you need this gamma element. Okay.
So this gamma element does this integration job.
In some sense. Okay.
Okay.
Okay. There is some situation where you can. Okay. There's a lot of situation where we can. This is basically in some sense this is the difficulty to integrate this k-homology part in the. Okay. There is exactly. Okay. Basically, I think that your question is in some sense is the following. So you have this exact sequence in the K theory, in the K theory, and you want to have the same exact sequence on the left hand side. I think that's your question more or less. And there is something which is quite difficult is to write the compatibility of the boundary of the two boundary maps indeed. You have the boundary maps in k-homology and this boundary map in K theory. And
compatibility with what?
With you have boundary map in k-homology.
Yes.
And you have this boundary map, this control boundary map, and okay, and you want some compatibility argument and this is exactly one of the difficulty indeed.
Okay. Thank you.
There is some okay in some situation we can okay we can solve the problem, but for the general case, this is the problem indeed. That the nature of these two objects is in some sense a little bit different.
Okay, thank you very much.
Okay, great. So I think it's the time to end this session of our seminar. Before we do it, let us thank our speaker again. Merci beaucoup.
Thank you.
Let me now stop recording.